Okay, this video is talking about work, energy, and power. So let's go back to our basic mass on a surface. And if I wanted to move this mass, I would obviously need to apply a force in one direction. And whenever you apply a force to an object, and that object moves some distance, we are doing what is called work. And work is equal to force times distance. Work is an uppercase W. And if we were to look at the units, we would see that it's newtons times meters. But for work and as energy, as we'll see, we replace a newton meter with a unit called a joule, which is an uppercase J. So work and energy is measured in units called joules. And so if I apply this force, and the force acts for a certain distance d, we can then determine how much work was done moving that block over that distance. Now it's important to note that in this case, only the parallel component of the force does any work. Okay? If the force is actually acting at some angle and has two components, so this is the perpendicular component and this is the parallel component, only the component that is parallel to the motion does work. The component that's perpendicular to the motion doesn't do any useful work unless there's a motion in that direction. So the work done is equal to the amount of energy, change in energy of this object. Okay? So work is also equal to change in energy. Okay? Remember this little triangle symbol, delta, is change in, and E for energy. So by applying this force over a distance d, I've changed the energy of this block. Okay? And so the work will equal the change in energy. And there's lots of different types of energy. The first type we're going to call potential energy. And potential energy is stored energy. So chemical energy is stored energy in the chemical components. Electrical energy could be stored in a capacitor or battery. The most common type that we're going to deal with is gravitational potential energy. And gravitational potential energy then is equal to, we're going to call it EP for potential, mg times h. So the force of gravity, the weight of the object, times h. And h is going to be equal to the height above the surface. Okay. So depending on where the surface is, even though the position of the object hasn't changed, if the height of it above the surface changes, its gravitational potential energy could change. So gravitational potential energy, mgh, again it's measured in joules, and it's the energy that's stored in the object due to its position above a surface. Okay? And it's stored energy because when released, that object will fall, and that energy can then be converted into a different type of energy, which we're going to call kinetic energy. And kinetic energy is energy due to motion. Okay? So as long as the object is moving, it has energy, and energy due to its motion. And kinetic energy, Ek, is going to be equal to 1/2 mv squared. Okay, so the speed of the object squared The faster the object's moving, the more energy it has, obviously. Okay? So whenever you do work on an object, you change its energy, either by increasing its gravitational potential energy when you lift it up, or by increasing its kinetic energy by pushing it and giving it some speed. Okay? So that change in energy is equal to the work done on that object. Okay, the final quantity that we want to talk about is power. And power is equal to the rate at which energy is used, or the rate of doing work. So power is equal to work divided by time. It's a rate. How fast are you doing work? And power is measured in units of watts, which unfortunately have an uppercase W as their symbol, and which is confusing because work is also an uppercase W, but power is measured in watts. And if you think about it, you've probably heard the term watt before if you've ever had to buy a light bulb. Light bulbs are often given in terms of their power rating. A lot of appliances, if you go and take a look at microwave ovens or refrigerators or any kind of kitchen appliance, will also list its power rating. So what they're telling you by giving you that power rating is how much energy it uses per second. Right? So for example, a 35 watt light bulb uses 35 joules of energy every second. Okay? So power is equal to work divided by time measured in watts. So it's a measure of how fast you're doing work. And something else that will be useful to us is efficiency. How efficient are we at doing work? And efficiency is equal to the work that you get out of a system divided by the work you put in multiplied by 100%. So you'll get a percent efficiency. Okay, so the work out divided by the work in times 100%. You could also put power out and power in times 100%, and the efficiency then would be a percentage. So you're converting 75% of the energy that you put in into energy that you get out. Okay, so those are the three quantities: work, energy, and power. In the next video, we'll talk about the law of conservation of energy.